let's give it 1 or 2 more minutes. But while we're waiting for the stragglers to come in, are there any kind of questions you'd like to ask? Because my plan today is to more or less follow the roadmap. And we went through partially some of the finals on last week. Uh, I'm going to go through primarily the packets today. So we'll go through the packets and exactly I'll highlight the critical components that I think are worthy of attention, especially with the final that's coming up. And I think because we're somewhat ahead of schedule, so I think we'll comfortably be able to review everything for the entire semester. So that shouldn't be a big deal. But are there any questions you'd like to ask me before we start today? Well, all right, let's get at it then. So the primary thing that we discussed last week is what are the components that are important to prepare for. So the handwritten notes, which are what we'll talk about the packets again today. The typed reader, I keep updating it. I'm on version number 27. So if you're looking in your B courses folder, you should be looking for 27.pdf. Hopefully you're not printing these things out. The typed up reader, the 2019 and 2020 finals, I've worked one of them out for you in depth. That's the 2019 one. And I believe Brian can go over during reading, writing, and review also some of the details on the 2020 final. Would that be okay, by the way? Brian, are you out there in the ether?
Yep, I can do that.
Super. He had to take it, so he knows it better than anybody. So the projects also, we'll go over that again, but I think they're fairly, we did that last week, but we can review that again if you wish. But I'd like to go through the packets 1 through 22 at today, unless you would like me to do something else in lieu of that. I mean, I'm happy to accede to your wishes. So would you like me to proceed with going over the packets and the details of the packets? Whatever you like. Does that work? All right, I see lots of thumbs up. So that is what I will attempt to do right now. So the packets, I mean, obviously have a sort of a coherent, rhyme to them. The first one in optimization theory, so this is packet number 1 that you're seeing online there. The key elements of this. So what I'll do in reviewing this is I'll first go through just a understanding of what the overall flow is of the packet. Then we'll come back and drill into details on this side of the board. So that's the plan today. So the idea in most of optimization and machine learning is the fact that you have some type of a cost function that's given by some type of a curve here in design space.
And of course, I think you need to share your screen. We're just seeing your camera.
Thank you so much. I always do that. I somehow seem to screw that up. So I should have been sharing quite some time ago. Just a moment. So again, what we'll talk about today, since I wasn't sharing my screen, is that we'll have basically the roadmap. And the roadmap is consisting of 22 packets, and we'll go through each one of those systematically right now. The first packet number 1, the main idea was as follows. So we'll do that now. Let me erase this. So this will be packet review. So the idea in most of optimization theory is we have some type of a curve that depends in a very nonlinear way on a design parameter lambda. Of course, for the multidimensional cases, this thing would of course be some type of surface in 3D that would be in multiple parameter space that would extend throughout the design domain. Of course, that's somewhat difficult to draw, so I'm keeping it here as a one-dimensional cost function with a one-dimensional or one single variable. But of course, our real objective is to actually go after this problem, which is that there's some type of cost function, which is essentially the error. So the error or the cost function is really want, have, divided by want, norm. That is usually what we refer to as the cost function. So there's something that we want the system to do, but when we guess what the parameters are, we have something that we're not quite, happy with. And the difference between the two and the appropriate norm, usually normalized by how big that want is, if it isn't zero, is typically a way to do a non-dimensional, measure of what simply the error is. So of course, our main problem is that the cost function depends usually on a design vector, and that design vector could be several thousand parameters. The parameters are listed 1 all the way to n. They're usually listed as a column vector. Lambda is considered to be the thing that we're trying to vary. Now, if we tried to do this brute force and simply said, well, fine, we'll just keep guessing what these parameters are, we'd have to be guessing a long time in multidimensional parameter space. So the classical approach in this kind of a method was to use the so-called gradient-based approaches. And gradient-based approaches make some critical assumptions. Number one, they claim that the cost function, or the assumption is that the cost function is convex. Simply what that means is it has some kind of a single minimum, where we know that if we take the gradient of pi and set it equal to 0 in multidimensional space, that we would be able to find the vector gradient of pi, which is partial of pi with respect to lambda 1, partial of pi with respect to lambda 2, all the way down to partial of pi with respect to lambda n. And that n by 1 vector then would be the thing that we would be trying to force to be the 0 vector. Okay. Now the problem is, of course, this is a nonlinear set of equations because pi is itself nonlinear, depends in a nonlinear way on all of these parameters. So this is not necessarily an easy task. So to be able to approach this in a systematic way, gradient-based methods simply start by saying, well, we want to impose that the gradient of pi is equal to 0. So we'll make a first guess at lambda to force that to happen. When that doesn't occur, that it's not equal to 0, we're going to expand the gradient of pi in a Taylor series. So our next guess, which we want to force to be equal to 0, is that we take the gradient of pi, we take its expansion, which is the gradient of pi, we expand that in a linear way. In other words, we keep a linear term in the Taylor series. So we have lambda I plus 1 minus lambda I. And we rearrange this equation to read as the gradient of pi multiplied times the difference between what we have and what we're going to guess as the new value is equal to the previous gradient of pi with a minus sign. And that, of course, occurs by taking this to the other side. This is set to be equal to 0. This is the remainder term on this side. And we have a system of equations where this rascal is called h, the Hessian. This is, of course, the design increment of what we have and what we're going to solve for. We have then the gradient of pi on the other side, and we solve the system of equations. Now, theoretically, this sounds like, well, it sounds pretty good. Let's do this. The problems are multiple fold. Number one, the function itself is usually going to be non-smooth. So the fact that we're going to attempt to take derivatives of it is kind of a fantasy, meaning that even just one gradient of pi, if pi really looks like a real industrial type of objective function, it's probably a mess and it's got all kinds of crazy wiggles. So taking a derivative of this thing is probably not going to be a good idea because it's going to oscillate like crazy, or it may not even be able to take one because the function is so non-smooth that at every place where there's a corner, the derivative is undefined. That notwithstanding, even if the function was slightly differentiable, we have to take a second derivative in this for this method to work. And typically that usually is going to really relegate this to simply a mathematical fantasy. It's going to be very difficult for that to be achieved in practice in industry. So the non-smoothness is one thing. Then, of course, we have other issues. So other issues are, for example, non-convexity. So non-convexity, and that simply means that these functions have lots of wiggles in them. So there's not going to be a unique minimum. And that, of course, is going to cause problems because that means that this matrix is going to be singular. It won't be invertible because we'll pass through inflection points. So that being the case, the gradient-based methods simply are somewhat doomed to relatively simple mathematical problems. One other concern, of course, is oftentimes when we're doing these kinds of optimizations, as you've encountered in the assignments during the semester, they're not closed form answers. So in other words, there's going to be some kind of a model. We're going to put in the parameter set and out pops up the performance. The problem is the model itself is not a closed form answer. So this thing is also going to have to require some type of simulation to run it. So the idea that if we take a model and we have to take its derivative because we have to compute, for example, gradients of pi, second derivative, the gradient of pi, that means that we're going to have to run the model over and over again to construct numerical derivatives to these kinds of functions. And I give you a taste of that in showing you here the numerical derivatives that occur here. This is also not an easy task. It starts to become a relatively complex affair where we have to also perturb the model multiple times to be able to construct this so-called Hessian here. So all of those things lead us to, the conclusion that we probably want to come up with some type of technique that has a couple of key features. First feature is it should be dealing with non-convex problems. That's a certainty. We need to deal with that. Number two, it shouldn't take any derivatives. So non-derivative type of approach. Those kinds of methods, have had a long history, roughly since 1974. The first one of this family was the so-called genetic algorithm, and I've given you a variation of that during this semester. And it's the first one of the precursor of many types of machine learning algorithms that are out there. And they're designed by their very nature to deal with problems that have all of these crazy kind of wiggles, bad behavior, and so forth. So as we know from the semester long of doing these types of problems, we take basically a parameter set, which is given sort of a pictorial image of like a piece of DNA or genetic material, a so-called genetic string. That's nothing other than just a visual representation of our vector lambda, which is our design vector. So the idea is we create a population of these. So what we do is we create a population of these little genetic critters that are all floating around in a petri dish. And in the petri dish, we make several of them at random within the design space. We then create a population. That's first. Then we evaluate the population. So we determine which ones are the best ones and which ones are the worst ones. Number three, we rank the population. So we basically determine which one of these are the best to the worst. Then what we do is we take the combinations of the best ones. So let's suppose these were the top two performers. We combine them in such a way that by now you're old pros at, you take all of the different pieces of material and we produce a child. Once we produce a child, we then take the children, recycle them back into the system, put them into the new population, and repeat this process over and over again. One key caveat is we, of course, kill off the poor performers. Okay. Now, this method as itself is, just a standard thing. And one of the key pieces of this class was to simply say, look, let's take this tool and apply it over and over again to many different possible applications. And you looked at quite a few different ones. You first started with the robot. Then we got into all of the different kinds of material optimization, process optimization. So there are a variety of different applications, which we'll go back and revisit shortly. But the main theme is always that same one as usual. Again, let's review just to make sure we're all on the same page. So step one, we basically create a population, and the population of S strings. Step two, we compute the fitness. So we compute the fitness. Now, of course, fitness is just another, analog to, really, it is the error. Okay, so how off are each of these different designs from achieving a goal we want? Then we rank them, according to performance. Then step 3, step 4, we mate the top parents and produce the children. Then step 5, we kill off poor performers. And then step 6, we repeat steps through 5, repeat until no more changes in optimum or certain number of generations. That's the hammer. And then we started looking for tools, right? Are there any questions on the process? Anything that might be bothering you at all? You go, you know what, now after 2 months of wrestling with this thing, I just had a question. Now it's time to ask. All right. I will go to the next thing. If there's no questions on this, we can do the same, the next one. Let me go to the next section. So packet number 2. So packet number 2 is artificial neural nets. Not covered, but very valuable. So neural nets, of course, they approach these kinds of problems, and they're usually applied to a completely different kind of problem, but still they're worthwhile just addressing very shortly. They're primarily interested in the following kind of paradigm. You have some types of input where you're going to put in the design variables, lambda 1, lambda 2, lambda 3, and so forth. And then you have a series of neurons and synapses and so forth, where the information from this design variable is fed in to all of the secondary layers of the neural net. Same thing with the information from here, also given to all of the information in the neural net. Same thing here, also neural net, and etc. And we go through this process. And once that design variable is taken in, it is processed by one of these neurons. So the idea, of course, is that some type of stimulus or piece of information is taken in here. It's processed. It could be a linear processor. It could be a sigmoid function processor, but some type of action is taken on that piece of material that is coming from that node. Then we go to the next layer and we repeat the process again. We construct information by taking information from all of these other previous layers, again, shown like this. And after going layer by layer by layer, ultimately we get down to the point where we take the output and we ask the following question. Is the output that we wanted for all of these inputs with weights given for each of these synapses and processing done by the neurons close to what our desired output is? If it is not, the widget that we have to attune or change is we can put different weights on the information that are processed here, and we can keep adjusting these weights over and over again until the adjusted weights produce something that is as close as possible to the output we desire. Now, 20 years ago, people laughed at this stuff and said, that's just a bunch of curve fitting with W's and synapses. This has no physical basis whatsoever, and you're never going to get all the data you need to be able to train these kinds of neural nets, shown nicer here on packet number 2, that'll ever achieve this. Of course, nobody ever had conceived of a cell phone, right? That was going to be everywhere. busily collecting data, or there would be an internet where people would be buying stuff right and left, and people could collect up their habits. But that really drove a whole new level of scrutiny and evolution of these types of neural nets. So they are really designed in for a very specific problem. Lots of data. If you have lots of data, the theory is that you can train the neural net and adjust the weights that are used to determine how much of this input is important to the output. If you do that properly and you train the weights, the conventional thinking is once the weights have been optimized of how much weighting there should be inside a neural net, it never changes. And then it's just becoming a synthetic brain, an artificial neural net, where the weights are already defined now, and now it's just a matter of taking different inputs and computing different outputs. Whether this is, genuine or not, or requires a massive amount of tuning is debatable. One cynical way of looking at this is that this is just simply nothing more than a large, elaborate, nonlinear curve fit or regression, where basically the widgets that you can tune are the processing in each of these nodes and the weights in which how much information gets transmitted through the synapses. I'm not a great fan of them, but I've coded them up before, and there is definitely some utility in doing them. But for most manufacturing problems, the plus up is relatively minor for optimization. However, they do have some purpose involved, but again, there are many more specialized classes to deal with this. For example, CS 189, 289, and so forth, but it wasn't an objective of the class. But I just bring it to your attention. I gave you the basic algorithm of how they work. So they're definitely worthwhile taking a look at if you're interested. But in general, for this class, it was not of a high priority. Packet number 3. So packet number 3, again, was more or less a review. It was essentially the main idea of what are the approximations to time derivatives. So for example, if we were going to take a time derivative of the velocity, dv dt, how can we approximate it? There are multiple ways. The simplest one, which is the one we used in this class, was to take v of t plus delta t minus v of t, divide by delta t, set this equal to whatever the function was on the other side at time t, then approximate v of t plus delta t is equal to v of t plus delta t times f of t, and proceed. Same thing with the position. It's r of t plus delta t minus r of t divided by delta t is equal to v of t. Then again, multiply times delta t, bring to the other side. R of t plus delta t is equal to r of t plus delta t times v of t. And that's how we proceed. So these two equations were the workhorses for most of our time-dependent time-stepping schemes whenever we encountered nonlinear differential equations. These are the so-called explicit time-stepping schemes. So explicit schemes. Now, explicit schemes, of course, have real issues. They need extremely small time steps. But that usually for manufacturing problems is perfectly acceptable, because usually the time steps are going to have to be in sync with some very complicated physical events. So if we're, for example, dropping material onto a floor bed, for example, maybe it's some powder sintering problem or a spray problem, the time steps have to be so small anyway because of the collisions of all of the pieces of material or the time steps at which a robot might be moving its robot arm around, that we already are going to use small time steps. So explicit methods are usually the ones that are used from the get-go. That is not necessarily the case in all of mathematical physics. there are many different other possibilities. And in the notes, I give you 3 or 4 different other possibilities: the backward Euler method, the forward Euler, which is the explicit method, and then of course, midpoint rules. It's debatable as to which one would be the best for a specific application, but if you're looking at applications where you have very detailed physics that is occurring at very small time steps, usually explicit methods are the ones that most people default to. Okay, so that's packet number 4, but again, more or less, I think review for most of you, but not necessarily something that's, completely emphasized as undergraduates, because of course the propagation of MATLAB and tools like that, you might default immediately to ODE 45 or some type of a time stepping scheme. So you have to be a little bit careful there to understand a little bit of what's going on under the hood. So packet number 4, the robot. So again, the robot, was a pretty good way to sort of, I guess, get our feet wet in terms of what we would like to deal with. The main idea there is that we have some type of kinematics of some types of arms. The kinematics are given by a coordinate system, x1, x2, x3. We have a servo motor at each of these junctions. And then we also have a dispenser that squirts out material here. And our idea was we want this robot to squirt out some type of a pattern onto a surface that we specify. So our objective is really that we have a position vector for the pattern we want, pattern desired, minus the pattern that the robot gave us, so pattern of the robot. We take the difference between those two, and we call that the error or the cost function. So this, of course, is tailor-made for our objective functions that have to do with optimization. And of course, our tool is the genetic algorithm. So our main issue here is we have a model, and our model is going to end up being the robot in this example. We're going to stick in a set of design parameters, compute the performance, and then keep repeatedly changing the parameters. They're changed, and then also simultaneously killing off poor performers, and then reinforcing good performance. So reinforce good performance. So again, our same genetic algorithm, we keep looping through here. Our main issue now really becomes the physics of the model problem of the robot. And again, in this case, to guide you through the packet, because of course I can't go through the whole thing, would take us a whole other semester to go through all the packets in detail. The main issues were twofold. Number one, we have the kinematics of the robot. So kinematics of robot. So the kinematics of the robot, were essentially that we took the position vector R1 that emanates along the first arm, called that R1. We have the position vector called R2. Of the second arm, we have the position vector of R3. And then we have, of course, the dispenser. So the idea is that R1 plus R2 plus R3 is the position of the dispenser. Then by taking the derivative, R1 dot plus R2 dot plus R3 dot is equal to R dispenser dot. That then gave us the velocity of the dispenser. So at that point, then that would give us the initial conditions for a piece of material that dropped out of the robot. The piece of material then are governed by the laws of physics. That would be m dv dt is equal to the summation of all the forces acting on that piece of material. And there were a couple of them. There was gravity. There was the drag terms. And then there was also potentially electromagnetic terms as well. So that leads to something where we group all of these together, and we call them just simply pitchfork total. right? And we call those the total forces acting on the system. At that point, then we have to solve for the trajectory of where this thing goes. The way we do that is just simply by taking mi dv, v of t plus delta t I minus v of I of t divided by delta t is equal to all of the forces acting on the particle itself at time t. And then we have v of I of t plus delta t is equal to v of I of t plus delta t divided by mi, total forces of I acting at t. We also then get the position of each of those little pieces of material. That's r of t plus delta t is equal to r of t plus delta t times v of I of t. So again, what that allows us to do then is we are allowed then to compute the trajectories of each of the particles, how they move through the system, how they splatter on the surface. And then all the rest are more or less physical details that I'll leave to you to review on your own time. But again, they're pretty standard undergraduate tools to put together. Our main issue then was this was a motivator for what came for the rest of the semester, that this model is simple, but, so then there's a but, we need to know more, right? So our knowing more is basically we need to get deeper and deeper into continuum mechanics. So I'll stop here for today because I think we need to kind of soak in a little bit more. I will proceed with packets 5 through, I'll try to actually get through almost all of the rest of the packets on Thursday. Then we can start to look at, for example, all of the different projects. We'll do that again the following week in reading, writing, and review week. And we can review anything you like, or if you simply want to have open office hours, we can have that. But I'll stop here for today. Brian, do we have any kind of more information you'd like to add about anything that I've talked about today?
I'm good on my side.
Any questions?
Will we go over the past exams? Like, for example, you could go through like each exam with us.
Yes, I'll happily do that. Probably that will be next Tuesday.
Okay.
Yeah, I'll go through
Thanks.
all of the exams very carefully to get you prepped and ready, because I believe the exam will be then released to you on Sunday of next week. Is that correct, Brian?
Yeah, that's correct.
Okay, thanks.
Sure, no problem. Well, all right then, just kind of don't get stressed out about finals and stuff. This class won't be the stressor. We'll finish comfortably. But please contact me if you need me, and I'll see you on Thursday.
Thanks, Tark. Have a great evening.
You too. Take care. Bye-bye.